Welcome back. We'll have the second lecture of our mini course series given by François Dahmani from Bordeaux, and he'll be speaking about automorphisms of free groups of small ranks and their outer conjugacy classes.
That's right. Thank you. Thank you, everyone, for being here, and the organizers. For bringing us all together for these 2 weeks. So today, I'll talk about automorphisms of free groups. Oh, let me try to write things. Okay. Okay, can you see? Who is speaking next? You? Okay, so you understood the rules of the game. Each time, one board left. Okay, so before talking about automorphisms of free groups, let's talk about free groups. And we already had the introduction about free groups, so I will go very easy on it. Free groups are fundamental groups of connected graphs. Okay. And there are also groups of reduced words. Okay. That means that I have an alphabet of R letters, and I write words with these letters, their formal inverses, and I write only reduced words, no pairs of inverse letter adjacent altogether. And then I concatenate, and then when I concatenate words, it's making the product of my group, but it's not reduced anymore, so I'm reducing, and it's a group. And it's the same thing as the previous ones, fundamental groups of connected graphs. So for instance, here is a connected graph. So if I look at the fundamental group, I should place a base point, right? But here there is only one vertex, so I just forget it. And the letters, those will be the petals. I think we have seen this before, but I can have more complicated graphs, like this one, with a base point. Okay, and now for finding what can be the letters to make my reduced words, or there are recipes for that. You have to choose a spanning tree, and then the missing edges will be the what makes the letters for your groups of reduced words. So that's the one way to move from one definition to the other. One very important thing is that this number are the number of letters that we'll need to describe the free group. Is an invariant of the group. It's always the same thing. And it's related to the Euler characteristic of the graph. Okay. Now we know what's a free group. Now, automorphisms of free groups. So already we are moving to part 2. And I want to just introduce Nielsen automorphisms. So F will be a finitely generated free group. So for instance, on R generators. And for convenience, so I will identify it with a group of reduced words. So W is for words, right? And I will describe, sorry, Nielsen automorphisms for F. It's an automorphism of a very simple form. It's either this one, oh, sorry. You choose an index and you map the letter of this index to its inverse and the other ones to themselves. Okay, so you just flipped one letter, or another kind of Nielsen automorphism, and you choose two indices, and you send xi0 on xi0, xi1, and all the rest on themselves. Okay, those are the Nielsen automorphisms. It's rather straightforward that they are automorphisms. And this observation has a consequence. Sorry. We know already this kind of automorphism in some other contexts. So if I take the Abelianization of the free group, okay. This induces a map on the automorphism groups. This later automorphism group is just isomorphic to GLRZ. And having spotted this automorphism, says that the map is surjective. There is another fact about Nielsen automorphisms that I won't really much use them other than in principle. It's that they generate the automorphism group of a free group. In particular, it's finitely generated. Okay. So far, I'm on schedule because I'm only giving no detail of general things. So I'm going to pass part 3. And since there are only 4 parts in this talk, it means that we are almost done. So, oh no, there are 5 parts, sorry. But we are almost done. Outer automorphism. I said I will talk about automorphisms of 3 groups, but actually we more often talk about outer automorphisms. The definition is very simple. First, I have to recall what is an inner automorphism. It's just an automorphism given by the conjugation by an element. They form a group of all inner automorphism, and out F is just, out G is just the group of automorphism quotiented by those ones that we are not interested in. So each time we could be interested in the automorphism group. It's interesting to look at the automorphism group in its own right, but very often we look at the outer, and in large part of what I will say, but not all, we'll talk about the outer automorphism group. So now when I will give some properties, classical properties that some automorphism, outer automorphism may or may not have, I will be slightly sloppy because I will often give as examples or examples automorphisms, or even in the notation there will be automorphisms, but the property that I will list here, they are properties of their outer class, of their class in the outer automorphism group, which is most of the time an easy check. Okay. Miscellaneous properties. So I should write that correctly. That outer automorphism may or may not have okay, and the first property I want to discuss, before that, I wanted to choose a notation. A principle of notations. So I will try to write Greek letters for this way for automorphisms. And capital, so here's phi, and capital phi, big phi, I don't know how to say, would stand for its outer class for the outer automorphisms of phi. Okay. Okay. Now, there we go. We'll say that an outer automorphism phi is fully irreducible. If yes, it's a class of phi. So it's a set of all phi times an inner. For the class of phi. Okay. So we'll say fully irreducible if, so what happens? If little phi as an automorphism does not preserve the conjugacy class of any free factor of f, and neither any of its power of little phi. So let me write that. So what did I just say? For all proper free factor, so meaning that there is another subgroup such that f is a free factor of both, and neither one is the entire group. And for all power of little phi as an automorphism that I want to apply to the subgroup, this is a subgroup of f, and I say it's not conjugate to A. Okay. Hey. I have to stop here. Why? Here? Here? There. I stop there. All right. So, example of a fully reducible automorphism. So example of what would not be a fully irreducible automorphism. That means, what if there is such a free factor that is actually preserved up to conjugacy by some power? Easy trick, you go to the Abelianization, and the free factor becomes a direct factor. So it means that I will see that on the matrix of phi in the abelianization, that there is this direct factor such that some power preserve it. Some power is no, I won't say trigonalizable. How do I say this triangular matrix by block. So it's easy to find matrices that don't have this property on Z, and it will suffice. So example, phi such that, okay, its image in GLR Z has no trigonalizable block, trigonalizable, power preserving a direct factor in Z. Okay. And in low rank, for instance, this such that its image in GLRZ has no power preserving a direct factor in ZR. That was the question? Okay. So for instance, in this, F2 generated by A and B, classically, A goes to B, B goes to BA. The matrix obtained has no invariant line in Z square. Z square. So, so this makes fully reducible easily achieved somehow. Another property, so properties, I made plural, properties of the outer automorphisms of F may or may not have. Perhaps some of them are fully irreducible and some of them are not. Another property is being atoroidal. So phi is atoroidal if it's similar looking in its expression, but instead of looking for the rather complicated notion of free factor, there are many possible free factors, sometimes a bit, okay. We are looking only on elements and conjugacy classes of elements. So perhaps I should have put this property first because it's more, in principle, elementary. So if for all G in F, for all M larger than 1, little phi of G is, little phi to the M, yeah, of G, its conjugacy class is not that of G. Okay. I will come back to why we call it atoroidal, so though I think that some of you can know or guess, but I'll come back later to the point of view of the suspensions that explain it. Examples. So first, non-examples. The the automorphisms of F2 here is not atoroidal. No automorphism of F2 is atoroidal. So, but why is that? We said that actually everything was going fine, stabilization, no line preserved. Yeah, because the culprit, the element that will be preserved, vanishes in the abelianization. So when I look at the commutator AB, so A inverse, A, B, A inverse, B inverse, and I look at its image, and I think, do I try to not be ridiculed in public by computing it now? I think it is sent on its inverse. Is it correct? No, it's not. Yes. Yes. Yeah. So when I do it twice, so let's call it phi, I don't know. Huh? Yes, when I do it, I choose a name for this, phi 0 square of A, B. It's not the same bracket. Bracket is commutator. It's not the bracket of conjugacy class. I hope you forgive me about this conflicting notation. How to find atoroidal elements? It's a good question. It's a bit complicated. What I can say, for instance, is that actually there are plenty of them, and they are generic in the sense that if you are doing choosing a random element through a random walk, you will end up with an atoroidal element. The reason is a little bit involved. First, and I'm saying that like very sketchy things, by hyperbolic geometry on certain spaces, you know that you will end up with a fully irreducible element. And then there is a result, I believe, Besvina-Handel, saying that in the case of fully irreducible elements, being atoroidal or being toroidal is very special, is preserving some kind of surface somewhere, preserving some kind of intersection form. In particular, when you map the elements in GLRZ, in the abelianization, you don't fall on everything of GLRZ, you fall on a very specific subgroup, SP. SP, I don't know, remember. I want to say R, but it's not R. Symplectic group inside of GLRZ. And this is very specific, and this does not happen for a generic element. That's what I just sketched briefly is a result of Kapovich-Rivin. I don't want to write it because we don't have the tool to write it yet. So it's just for general discussion. Next thing I want to talk about is topological realization of outer automorphism. So it's a property where all of them has it. So topological Okay, so for instance, the example I gave, it was using letters. And I started by saying three groups are really fundamental groups of graphs, connected graphs. And now it comes useful when I want to describe topologically an automorphism. So if F is a fundamental group of, well, I call it X, V0, X could be a connected graph. You will soon realize that I have only one picture for connected graph. It's this one. But there are plenty of connected graphs. The other day I was looking at the icosahedron on the shelf somewhere. And the one skeleton is a fantastic connected graph. And I thought I should bring the one skeleton, but you know, customs, have you anything to declare? I was insecure about that. And so you have plenty of examples of connected graph everywhere, given by that. And earlier I said, through the Euler characteristic, you find the rank. And it's funny to see how complicated it would, I mean, how tedious it would be to find the rank of the fundamental groups of these graphs if you didn't have this, this tool of Euler characteristic to say it at once. So I leave it as an exercise, but I mean, it's one-line exercise if you know, and probably you've done it on your head already. What's the rank of the fundamental group of the one skeleton of the icosahedron? Okay, but still, I will draw this for connected graphs till the end of the lecture. Not anything fancier. Okay, and if I take phi in hot F, or somewhere I have some vertex that I called V0 here. Realizing phi as an automorphism, so I told you, you first take a spanning tree. So realizing phi is finding a continuous map sending vertices on vertices. And inducing or sending V0 to V0 and inducing well, the automorphism. So what's the recipe to do that? Choose the identity on the spanning tree. So you already send all vertices on themselves, so you're fine with that. And then I told you that each of the remaining edge helps as a way to describe the letters in the corresponding expression as group of reduced words. So send the edges where they should go. Where they should go, it means that this edge E corresponds to a letter, an element of a basis of the group. I know where it should go by the automorphism. It goes to a word of letters of my alphabet. Then I want to write this word. But how do I do it? I have to start from this vertex, because this vertex is in T and is fixed. And perhaps E is sent to some word E1, E2, E3. So I start from this vertex and I want to meet E2. Perhaps E2 is here. Then I have a path in the spanning tree to go there, to go to the start of E2 and to the end of E2. And then I have to read E3. Perhaps E3 is here. So I arrive at some point, I have a path in the spanning tree that goes to the start of E3, and then I read E3. So I have a recipe to write my path, reading my words. So there are a lot of abuse of language in this sentence, and but I will not fix that. So by reading the word phi of E, so E is an edge, you have to identify it with a basis element, send it to the word with other basis elements, reading this word and translating into the path by the rule I sketched. Okay. It's a map. But, so I know it exists, but it's not so special. But, or I could choose any map that is homotopic to F, fixing V0. I should have called it F0. Choose F0 and F0. So I mean that the homotopy has to fix V0. Okay, but it's a burden. Why fixing a point when you can just like play with elastics all the way? What happens if I don't fix the point? I lose my base point in the group. What happens if the base point makes a loop? I'm doing a conjugation. Oh, that's an inner automorphism, by the way. So if I want to be more free to use all homotopy, I just step into outer automorphisms. So that was a long introduction for topological realization of outer automorphisms. I said and any map homotopic to this F0 without the necessity of fixing V0, freely homotopic will be a topological representative of big phi. Then we have a new tool to look at our automorphisms. And it's at least, so those are the homotopy equivalents of connected graphs. Look at the outer automorphisms. And it looks like other situation perhaps seen before, like outer automorphisms of surfaces. We know that they can all be realized by homeomorphisms of the surface, mapping classes of the surface. And there we go. A fundamental tool to use these topological representatives. I don't even want to write that. First, I have to say what is annoying in this situation. What is annoying in this situation compared to the case of surfaces? I just told you that actually, and you may take it as a fact, or you may know it, that every if you have a compact surface, a closed surface, every automorphisms or outer automorphisms of its fundamental group can be realized by a nice homeomorphism, diffeomorphism of the surface itself. Oh, that's very nice. So you can compose it and look at how the powers are going. And it's still, each time, a diffeomorphism. When you compose different things, you have to pay attention because it's up to homotopy. But here it's not homeomorphisms of the graph. Look, this edge E, its image, it went through all the orange path, twice sometimes. And even if I can do some homotopy after, no guarantee that I can remove the multiple images, that I can remove the lack of homeomorphy. Perhaps no guarantee that I can remove stupid simplifications so that when I'm using two edges and I'm looking at the path of their images, perhaps it cancels and I have to make a reduction. And of course, that's life. We know that happens with words. Words, they might cancel when they are concatenated. So that's a pain. And to treat this pain, there is the theory of train tracks. And I will stick to the most elementary first-hand train track object. This is a very wide theory with a lot of concepts in it. And yeah, but the first one I can take. So turn tracks will be special maps, special topological realization of certain automorphisms. And first, I want to define a turn. Okay, there will be a couple of like vocabulary words. I need to do that, right? So I will give credit with the main theorem. It's an invention of Betzwiener-Handel with Betzwiener-Fein-Handel going further. And okay, a lot of people. A turn in a graph. This is simply a pair of adjacent edges, oriented edges. What's that? That's the final vertex of E is the initial of E prime, and that's why it's a turn, because I can travel E and then perhaps turn and travel E prime. Yes. I'm sorry? Slightly bigger. Yeah, I can try. Yeah. Becomes more technical. It's time to. Huh? Oh, the small black eraser. Aha. Uh-huh. Perhaps. Okay. Now, if I have a map that is continuous, and that sends the vertices on the vertices, it tells me something about certain terms. It sorts which terms are good, which terms are bad. Okay, yeah, I assume something else of my applications, which is not the difficulty of all these things. This is easy to achieve. It is straightforward. I assume that the image of each edge is a reduced path. Yes, here they are oriented. From the beginning, they are oriented to distinguish X from X inverse, anyway. Yeah, I know I have to write bigger, but this is last. Now I write bigger. It's a black one. Okay. F can send an edge. So it sends an edge to a reduced path. So it can send a term to a reduced path or not. So we say that the turn is legal not this one, if it is sent on a reduced path. So it's legal for F. It will change if I change F, this notion, of course, changes. So that means that first, I have the, I should have used colors. First, I have the image of E, which is perhaps a long path, I don't know. And then the image of E prime. I want them not to start. I want it not to start by the last used edge. Well, it is illegal otherwise. And now, a train track map is a map sending vertices on vertices, reduced on edges, well, there are illegal turns. There are illegal turns. But the main thing is that there are no new illegal turns. It sends legal turns to legal turns. It's too low. Yes, legal means with respect to F. That's right. That's right. And I have some place here. I will add something just in a moment. But here I wanted to highlight where this is occurring. That means that this place is legal for F, implies that this place will be legal for F. This term will be legal for F. And I said I don't want to see no new illegal term. I want to add that edges not only are sent to reduced path, but to legal path. So that's a compatibility condition for the legality. All in all, this means that when I have a legal path here, I send it here, I have a legal path. There will be cancellations, but they are on the illegal terms, and they don't appear out of nowhere. They are here from the beginning. Okay. It's not at all obvious that such thing exists, and it's an important theorem in the field. If phi is fully irreducible, it admits a representative that is a train track. This means there exists X for which F is the fundamental group of X, and there exists a topological representative on this specific graph that is a train track map. You have to perhaps modify a little bit, fold the graph to find it. Okay. Now, what time do I have left? Okay. Now I want to pass to section 5, which I hope I have time to address at some point. But yeah. Oh, I have 17 there, but 20 there. Depending of the, okay. We'll see. But just before that, I want to illustrate growth on this situation, assuming that we are in this nice situation of having found a train track map on a specific graph for our fully irreducible automorphism. So I'm drawing my favorite graph. Is it the same as last time? You check. Same rank, at the very least, they have to be. Okay, those are the same. This is important because it's a self map. You have to be able to iterate it. And okay, somewhere in those places there are illegal terms. So there are graphical convention to write the illegal terms, but never mind. I want to take a legal loop. Perhaps there exists something like that. Perhaps I can move around my graph, and this is actually a fact, a part of the construction, and also consequence, I think, part of the construction at the very least, that I can find my way each time I arrive at a vertex There is no dead end. I can continue. And perhaps I have found one loop, only making legal turns. And that's a fact. There will be such a loop, even not very long, actually. And I want to know what its length here. Well, it depends on the length of my edges, but everything is sent on something legal. So there has no been cancellation. But still, I cannot say much because, well, I don't know where this edge is sent. This edge is very long. Perhaps it's sent on a tiny edge here. Yeah, I want to change the length of my edges and make this is a metric graph. And how to do so? I'm looking at the incidence matrix of F. What is it? It's a matrix, so row and columns are labeled by the edges. And at the coordinates E prime, I just write the number of times the image of E goes through E prime or E prime inverse. So I'm sorry, I was not clear enough. This time, but this is very rare in this talk, this time those are non-oriented edges for the incidence matrix. The rows and columns are the non-oriented edges, so the geometric edges, those are the one you see. And at the row E colon F, you write number of times the image of E goes through F. Either way, check. Well, what about this matrix? It's positive and it's, oh, you can apply Perron-Frobenius. It's irreducible, and you can apply Perron-Frobenius. What does Perron-Frobenius tell? The spectral radius, the maximum of the moduli of eigenvalues, is realized once by a positive eigenvalue, and its eigenvector can be chosen to be positive. I'll call it L, this eigenvector. It gives me a positive number for each geometric edge. What will I do with that? Those are the lengths. Those are the lengths of my edges in the metric graph that I want to define. And then what happens? Yeah. We call it M. So it's M E prime, E in the geometric edges. E prime also. What is M E prime? The number of E prime, occurrences of E prime, in the path F of E. Does it answer the question? Okay. Now I want to look at what happens to the length of an edge. Okay, define the length of geometric edges the length of E, I call it, length of E will be, well, the coordinate of the eigenvector, okay, positive. I have to choose one. I can choose one so that the sum of coordinates is one, but, or not, as you want. That will be L of E. Oh, L index E. You see, L is a vector, it has entries, the eth entry, yes. Oh, my automorphism is fully reducible from the beginning. So in this case, yes. In this case, yeah. I can apply for beyond Frobenius because of the irreducibility here. Yeah. And now I want to look at the length of f of E. Okay. So how to do that? F of E is a long path containing many edges, but those are all listed in the column of E of the matrix.
Sorry, can I just think of all length edges equal to 1? Why not?
No, you can't. Well, you can think of all edges equal to 1, but you won't arrive at my conclusion that I am craving for. I have only 7 minutes now. No, there is no guarantee that your map will send an edge to a path of same number of edges that the other ones. So we could send this one to one edge and this one to a pair of edges. Why not? This is totally possible. And so you will not have the same stretching property because, spoiler, I'm looking for a stretching property that I want to arrive there. You will have a combinatorial picture, not a metric picture. Oh, you can be happy with combinatorial. Okay, what's the length of f of v? So it's what is it? I collect all the edges inside f of v, and they are listed in the column of m corresponding to E. And for each of these edges, I must multiply by the length of the edge. So it is transpose of L times M times, well, I will call it E, where E is the matrix. Okay, I'm pretending that there were not numbers, but if I have to write the matrix, 0 everywhere, except 1 at the place E. Entries are labeled by edges. This gives you the column. This gives you the length. Okay. Oh. Yeah. So I missed something. I said something that was not good. And now I have no place to correct. So what happens? Trying to spot where what happens is wrong. L times M shall be lambda L. Because it's an eigenvector. And now I'm multiplying lambda L by E. I'm getting only one coordinate, which is lambda, the length of E. Yeah, so to do that, I have to apply Perron-Frobenius to the transpose of the incidence matrix. So L will be the eigenvector of the transpose. Sorry. Okay. Now you're happy?
You mean the left eigenvector?
Hmm?
You mean the transpose of them or the left eigenvector of them?
The left eigenvectors of them, yes.
Yeah.
Well, okay. I wanted to see the left eigenvector to apply this, and I didn't warn you beforehand that this was going to happen this way. So, I mean, right here, what is needed to be able to say that. Yes, you're right, Radhika. It's a positive left eigenvector. Okay. And you see that you have multiplied the length of each edge by lambda. Since legal paths don't have cancellation, you have multiplied the loop, the length of the legal loop, by this eigenvalue lambda, by this Perron-Frobenius eigenvalue. And this is the same for all legal paths. There is some growth that is occurring here that is the same for all the legal loops. And and this leads to, finally, fifth, growth. I will just introduce what it is, and I'll come back to this in the next lecture. Okay, let's P in out F and G in F. So definition, we say that the conjugacy class of G grows polynomially for phi if there exists d, the degree, or I should say 0, and there exists C, a constant, larger than 1, such that, I'm writing it here, I hope it's okay for, I write big, so such that for all n, the length of the conjugacy class of phi n of G is lower than C n to the D, So what is this? And I told you about this. That's the length of a cyclically reduced representative. Yeah, I have only one other definition to write if you allow me. That means I have 5 minutes? Oh, that's plenty. Oh, okay. Thank you. So for instance, and those Nielsen's automorphisms of the beginning, they are like that. They are polynomially growing on every element. But it's not what we just saw. We saw something that each time I apply f, I multiply by lambda larger than 1. So it's not polynomial growth, what we saw in the example of legal loops in train tracks. It's exponential growth. And yeah, that's the last definition. G grows exponentially for phi if okay, there exists lambda larger than 1, or I'll call it alpha, sorry, so to not to conflict with other notations, such that for all n, the length of the conjugacy class of phi n of G, I'll call it positive, is larger than alpha to the n. Alpha can depend on G. So I don't have to place length of G. If I want some uniformity, I will have to place this. And so examples, legal loops in train tracks. Of fully irreducible. And if I finish by a statement, the theorem of, do I have the 2 minutes to write the statement? And I'll come back to this statement to sketch the proof probably, but next time, is that there is some very peculiar phenomenon that occurs, that the elements, given a single automorphism, the elements that are of polynomial growth and of exponential growth, they arrange very nicely, and there are no other possibility. So that's a theorem of Leavitt, I believe, is that for all phi in out F, for all G in F, either G has exponential growth or G has polynomial growth, and there is more, moreover, I use this as a trick to get, can I state one statement? And so one bond, no. More of a, actually the polynomial growth elements, they occur in specific subgroups. There exist A1, AK, finitely generated subgroups of F, such that G has polynomial growth if and only if it intersects one of these groups. And I want to add something, that they are all of lesser rank. Actually, their sum of rank is less than the rank of F. If I write in this generality, I have to place less or equal. Okay. It's a very interesting theorem, mysterious for if you don't know more about it, because I didn't say how to approach this. I try to say a few words at the beginning of next lecture, so how to treat with that. Thank you, and sorry for overlapping. I'm sorry? Oh, there are only finitely many first. So yeah, so in general you cannot just hack the thing like that. But no, I don't need to. Well, there are more properties of this group that I could want to use at some point. But for now, I just there are finitely many such subgroups, and they are not so big. Yes, they depend on phi. For certain phi, if phi, we'll see that we'll see a reference for that next time. If phi is atoroidal, for instance, everything has exponential growth, or except the trivial element. The group generated by the legal loops.
Loops are conjugacy classes.
Conjugacy classes. Yes. Yes. So that makes. Okay. Yeah. Do I say anything? Well, most of the time it will be everything, but you can have a situation where you have a free factor on which you are polynomial. So you are not fully reducible. You have a free factor on which you are the identity. Well, I guess it makes the loops bigger. So you want to take a surface and
the boundary loop is not hidden. So
yes.
you're getting everything else is.
But you generate the surface with everything else.
Oh, yeah.
So perhaps you can cook situations in which you do not generate everything, but can K be related to the matrix of phi? Okay, you're talking about the matrix of a topological representative or the matrix of the abelianization? They're two different things. Abelianization. No. In the abelianization, you lose a lot of properties. So for instance, you have a whole a huge subgroup which is in the kernel of the abelianization, and in which you find fully reducible, blah blah. But you can also find the identity on free factors, and so you find all kind of phenomenon in these subgroups, and you see nothing on the abelianization matrix. That's yeah. So that's one of the pitfall of the examples I gave you. I gave, roughly speaking, a way to find examples of atoroidal elements, but all the examples found the way I proposed, well, the way Kapovich, Revin proposed, are non-trivial in the abelianization. Okay, the norm I define here is it's a cheap way to talk about length of words, of cyclically reduced words. And it's, if you want to see it in the graph, it would be to find the reduced loop representing your element. So once you found the reduced loop representing the element, that would be its length as a loop where all edges have length 1. But if you're looking at in a metric graph with the preferred metric as we cooked up with the eigenvalue and the eigenvector, those quantities will be related, but with some factor. So there will be a quasi-isometry between those lengths. Oh, inequality. So by the way, here is the expression of polynomial growth. So in the train track machinery, we more easily find the exponential growth. Yeah. So for legal loops, you see that in this statement here, for legal loops, you will have equality with lambda to the n times the length of G as a starting point for the metric graph that you cooked up. I'm sorry? G is fixed. You get equality over there in polynomial growth?
If you're fixing the loop.
Oh, it's fixed. You mean, yeah, if it's fixed. Yes. If it's fixed. We have some fixed loop, so contradicting atoroidality in the next lecture, because we have tori. Tell me that again, sorry. Yes. Yes. Yeah, that's right. That's part of the global exercise that I gently discard for myself to say that all the things I'm saying about out F, even though I'm using representative in out to express them, they are properties of the outer class. And as long as you are talking about the conjugacy classes of elements, you see that it does not depend of composing with an inner automorphism. So Yeah. Can every element of the free group be represented by a legal loop given the automorphism? No, in general, no. There are specific. Oh, it was, perhaps I misunderstood the question. Okay, it was a question, perhaps, okay. No, that's not true. You have elements that you cannot represent by legal loops, because if you could, they would grow exponentially. So for instance, take the initial example of automorphisms, A goes to B, B goes to BA. It's an automorphism of F2. I said it's fully reducible. You can believe me, I hope. But it's not toroidal. So there is an element that will not grow at all. So the degree of growth will be 0, and it's fixed by the square. So it cannot be represented by a legal loop in any train track map representing this automorphism.
One whose matrix in the abelianization does not have any, does not preserve any direct factor. Is the converse also true? Can there exist
Yeah.
maps,
Yeah.
matrix in the abelianization can preserve?
Yes, there are some whose metric and the difficult to say that matrix on the abelianization is trivial. There are such examples in the kernel of the congruence map.
Thank you.
Okay,
So if any more questions, okay, so let's thank the speaker. We'll meet back at 2.